Hi, in this session today, I'll be solving the Couette Flow example in COMSOL. So it's a time-dependent fluid problem that can be nicely shown here. I'll be doing this work in COMSOL 4.3. Okay, so I'll start. Uh, we'll be solving this problem in 2 dimensions to simplify our, uh, our calculation time here. I'm gonna hit next. I'll be choosing the laminar flow module. I can add that. You can see all the dependent variables that it'll be solving for. I'll hit next. I'll be doing a time dependent study. So I'll choose that and then I'll hit finish. Since I'll be working in small units, I want to create my channel rather small to have a low Reynolds number. I'll change my units in the geometry to millimeters. So first I'll build my channel. So I'll choose a rectangle. I'll say it's 20 millimeters wide and a height of 2 millimeters. I'll build the selected. Alright, now I also want to add a center line so that COMSOL will solve, we'll have to place nodes on that line and solve for them. And that just makes it easier later on to process the results. Alright, so under geometry, I'll choose the polygon here. I'll add linear. And I want it to start from 10 and at point 10 comma 0 and end at point 10 comma 2. So build the selected and there it is. I also want to add a few more points, so COMSOL will solve it at those points, and I want one at 10 comma 1. Alright, and also want to add it another point at 10 comma 1.5 millimeters. So you see the two points that I added there plus the line. Okay, so that won't affect the physics of it, but it's just so that it forces nodes to be there to solve for it. Alright, for materials now, I'll right click and I'll go into my library. There's already some built in, and I'll be just solving for water. So there's water, liquid, add it to my material, and it automatically chooses my entire domain 1 and 2. Now you see 2 green check marks, meaning it only needs the density and the dynamic viscosity here to solve this physics, so it's happy. Alright, and then just moving on the column, we go into laminar flow. Here I'm leaving it as a compressible flow, but if you want to simplify your calculations, you can also do an incompressible flow. And if you know you're well in the small Reynolds number regime, you can also check this to create a Stokes flow. Okay, but I'll just leave it as is and let it solve the way it is. So for my physics, you see here that it has already some fluid properties. So it has a Navier-Stokes equation with the viscous term in here, the full viscous term for a compressible fluid. It has the continuity equation as well. That's pretty much what it's solving for. It automatically adds wall boundary conditions and initial values to start its calculation. So I'll be adding an inlet. Let's say to my right. Left click on it. You see it turns red, and I'll right click to add it automatically. Now for my boundary condition, I'll be doing the pressure, no viscous stress, and I'll leave it at 0. And then I also need an outlet, so I'll choose an outlet and I'll choose the other end. And you see there, it's selected 9, and I'll leave it at pressure no viscous stress of 0 pascals. Alright, so now we see that the wall here, if we click on wall, we see that it's no longer includes the left and the right, since I've already moved those to become inlet outlet boundary conditions. The bottom will assume a no slip boundary condition, but since it's a Couette flow, I need my top boundary to oscillate in time. Alright, so for that, I'll add a new wall boundary condition, and under my no slip I'll choose a moving wall. Now you can tell it at what velocity it's moving. Since I want it to be oscillating in time, I'll give it a 0.5 millimeter amplitude with units of meters per second, and I'll multiply it by the sine of that. And now you see it's in yellow, meaning it's warning me that it doesn't. There's units that are off, or there's potentially something wrong. Now, although the amplitude is correct out here because it matches meters per second, it doesn't like the fact that 2 pi times t, the units will be seconds, but it understands that it needs to be unitless. So I'll give pi the units of 1 over seconds, and so it becomes a unitless function, and it's happy now. Alright, so that now I need to choose my boundary. So I'll choose 3, and I'll choose 8 to have it oscillating. Okay, and the mesh is fine as is. Now under time dependent, it's going to be solving starting from 0, solving to 1 second with steps of 0.1. But I want it to be a little bit finer, so 0.05 seconds. Alright, and then you can just right click and then hit compute. Okay, so you see here the solution. Now it automatically puts you into velocity, but the magnitude of the velocity. So it may be so a little bit better is to see just the x component. So under surface, under expression, I'll go under laminar flow, go into the velocity field, and check my x component, and I'll hit plot. Alright, now I'm going to set manually my color, my range in colors here. Alright, the reason I want to do this is because if I the range will constantly update, changing the scale, so you can't really tell the magnitude of the changing if your scale is constantly changing. So I want to leave that fixed so you can kind of get a good feel of how it's changing in time. Alright, so I'll leave the minimum of minus 0.001 and a maximum of 0.00 plus 1. Alright. Okay, so there it is. So it kind of sets the min and the max automatically. Now you can cycle through the times. Alright, so here you see under data set it says from parent. Now from parent is pointing to the velocity group, which is solution 1. Alright, so if you go back on the surface, you can just choose solution 1 here, and now you can choose which time you want to see it at, or it can also interpolate it for you between the points that you solve for. Alright, so if we start at 0, you see here we hit plot. Pretty much it's all static at 0, and then you know 0.2 seconds away, you see that the top plate has moved a little bit. Just choose another time, and you see it's kind of now going the other way. And you can see here that the velocity near the plate is kind of dragged along due to viscous stresses, while the fluid near the bottom of the channel, since it's too far away, it's longer than the viscous penetration length, doesn't really move down here. All right, so you can kind of see that pattern forming just by looking at this plot. But to kind of get a better feel for it, it'd be nice to see the amplitude of the amplitude of the oscillation of the velocity at certain distances away from the surface, from your top plate. So that was the reason we added points earlier, so we can visualize it now. So in the results, I'll hit the 1D plot group, and I want to look at velocities at points. So I'll choose a point graph. I'm going to choose these 4 points because I want to see the velocities at those 4 nodes. Alright, see 3, 4, 5, and 6 here. Alright, and I want the x component. So in the y-axis data, under laminar flow, the velocity field, I'll choose the x component again. Alright, and then I'll hit plot. So now you see the magnitude of the velocity in time. And you see here that the light blue represents the very top plate, very top of the plate, so that is oscillating with a large amplitude, and the red is a 0.5 millimeters away from the surface, and you can see the amplitude has dropped. And then when it's 1 millimeter away from the top plate, the amplitude is even less. And then when you're pretty much at the other end, at 2 millimeters away, the amplitude is 0. So you see that the amplitude is decaying as a function of distance, which is your viscous penetration length right here. And so that just kind of shows it to you very nicely as well. Alright, so now this is nice, but what would also be nice would be to see an animation. So we can also have an animation for our unit here. So you choose the plot that you want to see the animation here. So I'm going to choose my velocity. I'm going to zoom in a little bit. Alright, because whatever is inside this outer box here will be in the animation. So make sure that's where I want it to be. I'm going to right click export. I'll hit animation, and you can see here that's already pre-selected all of the times that it'll make into a movie. Alright, so it's going to, if you see up here, the output type will be a movie. So I'll save it on the desktop under the Couette Flow. And that should be it. So I should hit export. So now it'll save a file onto my desktop, and then it'll also open it in the Internet Explorer. So here it is. Here's the movie. So you can see here it's a nice little movie of the bottom is not it's not changing very much in velocity, while the top velocity of the fluid, you can see it's oscillating in time. So it goes from high to low and high to low, constantly back and forth. So you now have a nice little movie of it. Okay, and this kind of finishes up this Couette Flow example. Thanks for listening.